We present a novel approach for recording and computing panorama light fields. In contrast to previous methods, our approach is the first that processes ray entries directly and does not require depth reconstruction or matching of image features. Therefore, arbitrarily complex scenes can be captured while preserving correct occlusion boundaries, anisotropic reflections, refractions, and other light effects that go beyond diffuse reflections of Lambertian surfaces. The displayed panorama light field was recorded with an off-the-shelf panoptic camera in approximately 5 minutes. We compared our method with two alternative approaches. This example shows refocusing of a panorama light field computed with a naive image stitching of corresponding input light field perspectives. In this case, the independent processing of the light field's spatial and directional domains leads to strong refocusing artifacts. This is not the case for our method, as shown on the right. Another approach converts input light fields to focal stacks and applies simple image stitching and linear view synthesis to derive panorama light fields. This, however, covers no more than a 3D subset of the full 4D light field and causes artifacts at occlusion boundaries, as shown in this example. Furthermore, focal stack stitching is not able to preserve correct anisotropic reflections and refractions. Our approach produces correct panorama light fields that contain all information recorded in the original input light fields. These color-coded difference images illustrate the variation between leftmost and rightmost light field perspectives. Comparing with the difference image of the original input light fields as ground truths reveals what is lost with focal stack stitching. Our method preserves all initially captured light effects. For recording, we prototyped a panoramic tripod head for panoptic cameras. It has been 3D printed and supports adjusting the distance between the camera and the rotation axis with an adjustable slide, and allows exact rotations. How the optimal camera distance and rotation offsets with respect to the desired optical settings of the panoptic camera are derived is described in the paper. We also use these derived parameters as initial guess for registration. This example shows the overlapping projections of two input light fields for the center perspective of the panorama using the initial guess. The ideal camera distance and rotation offsets are found in two interlaced optimization steps that minimize the integral root mean square per pixel luminance error of the overlapping projections. After all input light fields have been registered, the rays need to be converted from individual two-plane parameterizations to a common cylindrical parameterization. This is explained in more detail in the paper. For each cylindrical panorama perspective, we select and transform the necessary rays of all input light fields. The rays of the same input light field are linearly weighted with a head function before they are alpha blended with other input light fields to result in the same panorama perspective. We present the first panorama light field imaging approach that processes ray entries directly instead of perspective images or focal stacks. It does not require depth reconstruction or matching of image features and can capture arbitrarily complex scenes while preserving correct occlusion boundaries, anisotropic reflections, refractions, and other light effects that go beyond diffuse reflections of Lambertian surfaces. Our technique determines the optimal recording parameters with respect to the desired optical camera settings. Together with our panoramic tripod head and off-the-shelf panoptic cameras, light field panoramas can easily be recorded in a matter of a few minutes. We explain the one-time pre-calibration of panoptic cameras and how input light fields are correctly registered, blended and parameterized. The rest of the video presents more results.